Good morning, everyone, and welcome to the third annual Breakthrough Breakfast hosted by the Faculty of Engineering and Design. Thank you for joining us here today. My name is Audrey Gerward. I'm a professor in the School of Information Technology at Carleton. We're joined this morning by alumni, industry partners, faculty, current students, and members of our community. Today's virtual breakfast is one of many events hosted across the city of Ottawa as part of International Women's Week, spearheaded by local organization Invest Ottawa. It's too bad that we can't share a meal together, but I have my Carleton mug with warm tea inside, and I'm ready to get started. This morning, we have the opportunity to hear from two outstanding graduate level women researchers at Carleton, along with an exceptional postdoc researcher. So I'm a human-computer interaction researcher. My research is pioneering novel interaction techniques with our devices through shape. Deformable and shape-changing devices offer users the ability to physically manipulate objects to interact with them, which in turn offers new interaction techniques to users. When wearable devices can integrate the body or our clothes, this can make the interaction more ubiquitous. These devices offer interaction opportunities in many domains, such as making or gaming, and they may be particularly interesting for people with disabilities, offering complementary inputs to the widely available ones. So my interest in engineering and science began at a young age. I was fascinated by science experiments. I was reading the kids' science magazine, Les Débrouillards, religiously, and 30 years later, it's a favorite in my house again with my own kids. They're actually doing a science experiment about water upstairs while I'm with you in this breakthrough breakfast. So we know that exposing and encouraging girls at a young age to STEM activities, providing them with role models and educating them on the career path available to STEM graduates is critical to changing perception and contradictory stereotypes. I've had the opportunity to give talks to elementary and high school students about the research I do, as well as the different careers that exist for women within engineering, within science. It's important for them to hear about the variety of science and engineering possible, because there's many amazing opportunities where sciences can be applied to other areas. Working in partnership with industry and higher education institutions across the country, Carleton and the Faculty of Engineering and Design is proud to be a champion of 30 by 30 and is committed to initiatives and events like today's, which celebrate diversity and inclusion. Through significant engagement with youth in the community, including specialized programs for young women and girls run through our not-for-profit organization, Virtual Ventures, tailored engineering recruitment outreach, and close collaboration with industry and alumni, our faculty is invested in fostering a passion for STEM fields early in life and ensuring support for our students throughout their academic careers. Just this past week, Carleton officially launched its all-new Women in Engineering and Information Technology program, one of the first sponsored program of its kind in Canada, led by the Faculty of Engineering and Design with financial support from industry and government partners, many of whom are joining us here today. I would like to thank all of the partners supporting this groundbreaking program, which will provide learning and development opportunities for both undergraduate and graduate level women within Carleton's wide range of engineering and information technology programs. In founding this collaborative initiative, together we will establish a comprehensive network of women ambassadors and volunteers and provide the necessary tools and knowledge for women students to successfully transition into the workforce. There are so many talented women at Carleton University, and I look forward to welcoming many remarkable women to the Carleton University research community within the 10+ years as we move closer to our national goals by 2030. This 30 by 30 goal of Canada's engineering community is well aligned with this year's campaign message for International Women's Day, Balance for Better. Countless studies demonstrate that a balanced and diverse workforce, or in this case of a university setting, a classroom or a research environment, achieves better results. Diverse ideas will better the world, not only for women, but for everyone. So before we get underway with our featured presentation, I'd like to quickly remind everyone to type in any questions you would like to ask our speakers as they come to mind using the chat box. We will try to get to as many questions as possible, but please be mindful that we may not be able to answer all of them due to a high volume of questions. So at this time, I would like to turn the floor over to our first speaker, Brittany Allison, a Master of Applied Science in Computer and Electrical Engineering at Carleton University. Her research in integrated circuits and high-speed communication links focuses on improving both internet access and speed in relation to the increased demand for high-speed internet brought about by more people working from home during this ongoing pandemic. Welcome, Brittany.
Thank you. Good morning, everyone. Today, I would like to speak to you about my experience at Carleton and some of the research I've been doing, specifically the applications towards internet speeds and data centers. Just under 5 billion people are using the internet. The amount of data being generated each day is difficult to comprehend. The average consumer, myself included, does not put much thought into data management or network infrastructure. This is because the internet is marketed as information floating amongst the clouds, waiting to be summoned to our computer screen. In reality, this is not the case. All that information has a physical location, and more often than not, that's going to be inside of a data center. So today, I want to look at a simple example, the story behind an internet search, and more specifically, what happens from a hardware perspective now that we all know that data is not floating in the sky. So I'm sure everyone knows what a Google search looks like, but today I would like to focus your attention to the orange box, which reads 1.6 billion results in 0.79 seconds. This is very fast, but I'm sure we've all experienced internet lagging at one point or another. So let's look over this simple example and ask yourself some questions. 1, where did our request go? 2, where did the result populate from? And 3, most importantly, what happened in that 0.79 seconds? And this is the adventure I'd like to take you on. Our first step is inside your computer. After pushing enter, your computer sends the request through these small green wires from one part of your computer to the other. And then your computer has to decide where in the world this information is being stored. And similar to you and I, your computer does not know. So the next step is to send a request to a domain name system server, or DNS, which works like an address book. We send a request to the DNS, and it looks up the IP address. And more often than not, this is going to be inside of a data center. And a data center is a facility filled with computers, servers, routers, and much more. The purpose is to house and distribute data or information. So to recap, our request goes from our computer to the DNS server, which directs our computer to the appropriate data center. Now I'm hoping that you're impressed that all of this has happened in less than a second. But if you remember, this is only one of our 1.6 billion results. There's a lot of software and algorithms out there to optimize this process. But as you can see, if all this needs to happen for a simple internet search, how data traffic can really accumulate once you start attending virtual meetings or streaming videos online. Fortunately, when we're sending data over long distances, we normally use fiber optic cables, which transmit data nearly at the speed of light. So it turns out the bottleneck in our process is actually in the electrical links, the small wires traveling from one chip to another. And these electrical links are what your computer, the DNS server, and the data centers are all comprised of. They're everywhere. And this is specifically where I do my research in high-speed communication links. The most common method is called SerDes. It takes parallel information, serializes it, sends that data through a channel, and then deserializes. The main advantage is eliminating the cost of interconnections and cabling if we would have had parallel wires for each bit. So what would happen if we did not use SerDes? The image on the left would get sent through the wire, and we would receive the image on the right, which looks like static, and it's not at all representative of what we transmitted. What's the point of delivering high speeds if we cannot have accurate information? Let's find out why this happens, a brief solution, and then we'll focus on increasing speeds. This happens because the loss in the channel is dependent on frequency. So as we're increasing that frequency or as we're increasing those internet speeds, we're going to get more and more loss. This causes intersymbol interference. And interference is comprised of two main issues. amplitude loss, which causes our 1 bits to become much lower. And secondly is incorrect timing, which causes our 1 bits to kind of get smeared out with time. And this is called dispersion. The issue arises when you transmit 2 1 bits in close proximity. The dispersion from the 2 bits gets added together and cause inaccurate data. This is why it's called interference. And interference becomes a very big problem in SEERDs. The main technique to remove interference is called equalization, and it can be found in both the transmitter and the receiver. The transmitter uses an equalizer to reduce the dispersion caused before the 1 bits. And now we have to equalize the interference caused after the 1 bits. And this happens in the receiver. The equalizer in the receiver increases the amplitude of the 1 bits and reduces the remaining dispersion. We can see that the received signal is now representative of what we transmitted. Unfortunately, this is only half the puzzle, but now that we're all experts in sending accurate signals, we can look at the other half, which is timing. And timing is directly related to speed. To get the 1s and 0s, we need to sample each bit. We take a sample of the data at each tick of the clock. And to increase data speeds, we need to increase sampling speeds. Unfortunately, if we try to increase the clock speed, we accumulate errors with time. And as you can see, this can corrupt our data. Now, without going into the specifics, the 2 new blocks that we added to our system correct and avoid these timing issues. The PLL specifically increases the sampling rate without having to increase the clock rate. Now we have done all this work so that one chip can talk to another. This year, my research team created a system at 80 gigabits per second. My phone holds 64 gigabytes. This means the entire content on my phone can be transferred in just a few seconds. Every few years, researchers like myself develop new techniques to create systems at higher speeds. Currently, there is a push to create standard speeds at 100 gigabits per second. And within 5 years, these standard speeds will double to 200 gigabits per second and beyond. This is great news, except increasing the speeds also increase the power. So if you remember this graph, it shows the loss at different frequencies. The power increases with speed to compensate for the increased timing error as we increase those sampling speeds and the increased interference as we fall further down the slope. So let's do some simple math to find out why this is a problem. 1 gigabit per second costs approximately 1 milliwatt. Currently, we have speeds at 100 gigabits per second, which costs 100 milliwatts. If speeds increase to 200 gigabits per second, then we'll have to increase our power consumption by 100 milliwatts within just a few years. Now, 100 milliwatts is not a lot of power, but let's zoom out and see the big picture and find out how this number really accumulates. SERDES are used for chips to talk to other chips, as well as these vertical line cards to talk to the green board or backplane that they're plugged into. This is an example of a memory module, which could be used to hold information from maybe a website. These memory modules live inside of the server. As you can see, there's a lot of other components to these servers. Some of these components may need to communicate at high speed and might also utilize SERDES. Each server is stored inside of a server rack. The wires connecting the servers may also need to communicate at high speeds, again, utilizing SERDES. And here's a small hallway of server racks. And this hallway is one very small part of this Google data center. This is one of many data centers all over the world. Let's say that there's 1 million SERDES inside this data center. I believe that there's a lot more, but we'll take this as a conservative guess. And we have to increase the power of each one of those SERDES by 100 milliwatts. This would consume an additional 100,000 watts. Now today, we only discussed the distribution of data at high speeds, and we have not even yet considered what it takes to create or store data at equally high speeds. So hopefully you can start to imagine how much power a data center can consume. Actually, in February 2019, it was predicted that by the year 2030, data centers would account for 8% of the world's total energy usage. With many people transitioning to working from home due to COVID-19, network connectivity at high speeds has never been more important. It's possible that data center energy usage will rise beyond 8%. Therefore, it's critical to develop power-efficient circuits to be used within these data centers, a key goal of this research. Thank you, and happy International Women's Week.
Thank you, Brittany. This was very interesting. So our next speaker today is Emma Farago, a PhD student in electrical engineering at Carleton University. Her research interest includes developing wearable assistive devices and biomedical signal processing. Her thesis involves signal quality analysis of electromyograms, so muscle signals, to improve smart assistive and rehabilitative devices.
Thank you for that introduction. I'm really excited to talk about my research, and I call my presentation Building Better Robots because I think my work will help us to build better robots. So just some personal background. When I started my university journey, I wasn't sure what I wanted to do. So I knew I wanted to do research. So I pursued a Bachelor of Science in Medical Sciences. But later on, I started to realize I wanted to focus on practical applications, helping people, and using math and technology. So I ended up switching into electrical engineering, going down that path. I completed my master's in electrical engineering, helping to design wearable devices to assist with rehabilitation. And now I'm currently working with Dr. Adrian Chan in the EDC Chan Lab, doing a PhD in electrical engineering and specifically working with signal quality. So when I first started thinking about wearable robots, I often thought of all of the cool devices you can see in the movies. So Luke's arm from Star Wars, the exoskeleton that Iron Man has, and I found out there's Iron Woman for Women's Day. So there's a lot out there, but it's actually not that easy to build something like this. So all of these devices are wearable and they would work using your muscles. So what my research focuses on are electromyography signals, which are basically muscle signals or signals produced by the electrical activity of the muscles. So in this picture, we have the setup that you would have to measure muscle activity. So here we have an arm and it has electrodes on it. And the arm isn't contracting right now, so we're not seeing any signal. But when someone contracts their arm, electrical activity is produced by the muscles, and then we can start to see more of a signal over here. So when a person is fully contracting, we'll see the largest amount of signal. So these electrical signals are very small. They're less than 1 millivolt. We can amplify them to 1 volt, but to put that in perspective, a battery is about 1.5 volts. So this is a very small signal that we're looking at. So that can cause some problems. So a few practical applications for EMG signals. The first one is controlling an exoskeleton prosthetic. So in this example, we have a prototype for a prosthetic and it will be a hand. So what we have here are a band of electrodes around the forearm. So if you want, you can put your hand actually on your forearm and try moving your individual fingers. You should be able to somewhat feel your muscles moving. So what this electrode band is doing is measuring the activity of the muscles when a person is moving their forearm. From this, we can infer how the hand should move. Another application with wearable devices is applying electrodes to the body and then having someone move. So this could be done for sports to make sure an athlete is activating the correct muscles during an exercise, but it could also be done for rehabilitation to make sure someone is proceeding in their therapy correctly. But the big problem with this, as I said before, is EMG signals are very small. So what my research is involved with is making sure we have a good signal or the problem of signal quality. So since EMG signals are very small, they can have a lot of contamination in them. So a few sources of contamination could include other signals in the body. So the heart also produces electrical signals every time it beats. They look like this, and they can interfere with your muscle signals when we're trying to measure them. Another source of noise can be movement. So if someone is wearing a wearable robot that's trying to measure their muscle signals, they're probably moving. So when you're moving, these electrodes on your body can start to shake or jiggle, and this could disrupt the signal we're trying to actually measure. We also can have random noises from the environment, like white noise, or even power line noise. So there's a lot of sources of contamination that can affect these signals. So I want to do a poll, and I want you to tell me which signal you think is better. So one of these signals is an actual EMG signal, and the other is just white noise. So hopefully you can see on your screen that there's a poll. Okay, so most people picked A. That's pretty good. So A is actually the correct answer, so good job. But I hope you can see that this is actually a kind of hard problem to solve. So EMG, the signal itself, actually looks a lot like noise. So it's not that easy to tell the difference in some cases. So how this is done can be done through engineering and AI and machine learning techniques. So what I'm trying to work on is designing ways to tell if a signal is good or bad. So in this example, we have an EMG signal, and we can use artificial intelligence, basically use computer technology, algorithms, machine learning to determine, is this a good signal or is it a bad signal? The other benefit of this is that we don't need a human to be looking at these signals every time. We can automate the process to make it faster and so that it will work in real time. So a wearable device or prosthetic can determine which signals are good or which signals should not be considered. So let's try one more poll. I want to know again which signal you think is better. Okay, so most people picked A, and A again is the correct answer. So I chose this example because I wanted to show that it sometimes is easy to tell the difference, or at least see the difference. So the first example, I tried to make it a bit harder. But what's going on here is you have actually 3 separate contractions. So these are the regions when the person was activating their muscle, and the flat area is when the person was not activating their muscle. So if someone's not moving, we don't want to see a large signal. So that's why this is kind of close to 0. The problem is here, we have a lot of signal going on, even though the person isn't moving. So this is most likely noise. So that's one of the ways that we could detect which signal is actually the better signal to look at. The other area of research I'm focusing on involves electrode placement. So when we want to measure muscle signals, we need to ensure the electrodes are put on the body in the appropriate spot. So this can be a pretty difficult problem if you want to measure, say, the body of an athlete. You need to know, where should I put these signals on the muscles? And there are a lot of muscles on the body, so it's not that easy to do, even if you are an expert. So for the average person, they might not know, where should I put these electrodes? So what I want to do is simplify this process so that anyone can use this technology, whether it's for sports, for rehabilitation, or to improve prosthetics. So what we can do instead is develop an electrode array. So instead of having just 1 or 2 electrodes on the muscle that have to be in a specific spot, we could put an array of electrodes over the muscle. Then we could use AI technology to determine which electrodes are providing high quality signals and use those signals to control the device or to assess muscle activation. So that will really improve the quality of the signals that we are putting into the device. So in conclusion, signal quality is one of the most important steps to building a practical wearable robot. And I think most people might not think of that as a problem, but it really is important for making a robot we can control with our body. So if we continue on with signal quality research, we will be able to create prosthetics with increased robustness and user satisfaction, and allow people with disabilities to participate more fully in society. So I would like to thank my supervisor, Dr. Adrian Chan, another co-supervisor, Dr. Don McIsaac, and all the members of the ADC Chan Lab for their support. I would also like to thank the organizations that helped to fund my research. So that includes the READY program at Carleton, Carleton University, and NSERC. So thank you so much for listening to my talk today.
Thank you, Emma. Great talk. So our final presentation today comes from Dr. Jin Kang, a postdoctoral researcher with me in the Creative and Action Labs at Carleton. She investigates how media and communication technologies can be designed to promote individuals' overall well-being and to encourage individuals to achieve their better selves. In this talk, she will specifically talk about her project on chatbots, social media, and wearable trackers that fall within this overarching research agenda.
Thank you, Audrey. Thank you, Audrey, for the introduction. Hi, everyone. It's really great to be here today. So as Audrey has mentioned, I study all sorts of communication and media technologies, and I specifically investigate how their unique characteristics can be used to facilitate positive behavioral, cognitive, and emotional changes in people. So communication technologies, broadly defined, include those technologies that allow you to interact with other people. So social media and video games are really good examples of communication technologies. And communication technologies are also, they directly interact with users. So for instance, chatbots, Alexa, and even wearable trackers are also good examples of communication technologies. So I focus on the source characteristics of these communication technologies by asking questions such as, should a chatbot be emotionally intelligent, or should a video game avatar look like a player's ideal self? I also focus on their message characteristics by asking questions such as, how should we frame wearable tracker reminders to motivate the logging behavior in users? And lastly, I also examine affordances by asking questions such as, what is the effect of customization and personalization in fostering positive user attitude towards a website? So today I want to share with you two projects I think that best represents my overall research direction. So the first project is on persuasive fitness app reminders. So just a bit of background. So we know that these wearable trackers and mobile fitness apps, they can actually bring people with a lot of physical and psychological benefits. However, all these benefits are only possible if people continuously track their targeted information. And so to encourage, this continuous tracking, these devices send people with multiple reminders every day, right? So, you get reminders to, enter your dinner. You get reminders to enter your water intake, and also the reminders to, which type of exercise that you did after eating lunch, all sorts of reminders. But unfortunately, research indicates that people actually do not listen to these reminders, and therefore they always fail to track their important information. So that observation is what motivated my colleague and I to ask the following research question. So what make fitness reminders persuasive? So our study was really straightforward, where we asked 100 participants to design their own fitness app reminder that would motivate them to log one of the 5 following behaviors: breakfast, lunch, dinner, weight, and exercise. And here is a brief summary of what we have found. We found that our participants, they designed reminders that mentioned their specific goals. So that is the reason, like why they were tracking their particular behaviors. And they also designed reminders, they were humorous, and they also designed reminders that, seemed like they're getting text from their friends. So right now with this project, my colleague and I are planning for study number 2, where we are trying to build an actual fitness app. And we plan to have one group of people who will use this app for over a period of 2 weeks, and they will actually receive reminders that will be created based on our findings in study 1. And we'll also have another group of people who will use the exactly same app, but for them, they will actually receive reminders that are available in the current market. So at the end of the day, our goal is to compare these two types of groups on how they're different in their tracking behaviors. And I think that that type of data will really give us greater confidence that the message features that we have uncovered in study 1 are truly persuasive and effective in motivating people to log their important information on wearable trackers and also on fitness app. So I will now move on to talk about project 2 on chatbots and personalized social support. So, nowadays chatbots, not just chatbots, but all conversational agents, they occupy really, meaningful and intimate social roles. They are our personal friends. They are also our personal therapists, and also some of them are our personal tutors. And these type of chatbots that occupy these meaningful social roles, they are really good at providing people with two types of social support. One, informational social support, and second, emotional social support. So in this particular project, my colleague and I investigated whether people would trust the chatbot that provide them with personalized social support more compared to the chatbot that provide them with non-personalized social support. So now I'm just briefly going to define what I mean by personalized and non-personalized social support. So personalized social support is when there is a match between the person's general social support preference and the actual support given by another human being or by a chatbot. There are people who generally prefer to receive emotional social support when they're stressed, and therefore they are just much happier after getting emotional social support from another entity. And also we have another group of people who generally likes to receive informational social support when they're stressed, and therefore they will be much happier after receiving informational social support from another entity. On the other hand, when it comes to non-personalized social support, it is when there is a mismatch between a person's social support preference and the actual support given by another entity. And as you can imagine, when a person receives non-personalized social support when they're stressed, one can predict that they will actually become even more stressed and actually be less happier because they're not getting the type of support that they generally prefer to get. So in order to test those exciting hypotheses, we recruited and actually classified participants as either having emotional or informational support preference. And after this classification, all participants interacted with a simple rule-based chatbot that provided them with either personalized or non-personalized social support. So I'm just going to walk you through with a brief summary of the key findings. So when it comes to participants with informational social support preference, receiving personalized or non-personalized social support actually did not matter. That is, these individuals, they trusted the chatbots equally after receiving both emotional and informational social support. However, the interesting thing about our result is this. When it came to people, participants with emotional social support needs, they actually trusted the chatbot that provided them with personalized social support more compared to the chatbot that provided them with non-personalized social support. So for these individuals, the chatbots that provided them with a personalized social support were much more liked and trusted compared to the chatbot that provided them with non-personalized social support. So I think this finding is really fascinating. That shows how the effect of a chatbot's personalized and non-personalized social support differs based on people's individual characteristics. So in this study, the individual characteristic being their general social support preference. So I hope these two projects, give you a bit of sense of what I do. And, if you have any questions about these two projects or any other projects that I have stored in future, please ask me questions. Thank you very much. Again, thank you for having me today.
Thank you, Jen. Great presentation. So we're moving on to the Q&A portion of this event. If you have questions, feel free to submit them in the Q&A box. There's already quite a few there, so we're gonna get started right away. So the first question is to Brittany. Why am I only getting around 1 gigabyte per second internet speeds at home? This is much lower than the speeds you were discussing.
Well, the reason this happens is because the applications I was talking about today was for those expensive high-speed data centers, when it really comes down to a battle of cost versus speed. And when it comes to those data centers, the speed normally wins. So the companies will pay to get the infrastructure for those high speeds. When it comes to residential homes, the network providers normally cost wins, and they're not willing to pay to get you the infrastructure you need at your home.
Thank you. So next question is for Emma. This is from Anna Kra. So once the best location of the sensors are determined, would there be a way to temporarily or semi-permanently tattoo a key on the body and the device to ensure a good fit every time? I'm particularly thinking about rehab application. Perhaps this is already something you're doing.
Sorry, I was on mute. So that's an interesting question, which I haven't actually done. So there's a couple of things that kind of gave me a red flag at first, is tattooing something on someone's body. I don't know how many people want that, especially if you're just doing rehabilitation. It might not be a good idea. The other reason I think it might not be a good idea is putting the placement is not the only factor. So it could also be random noise or poorly placed electrodes. So I don't know if that would be always a good factor, or since people change every day, if that would work well over time. So that's an interesting idea. I'm not sure how well it would work in practice, but for that suggestion.
Great. So next question is for Jen from Megan. Is there cultural differences between how people want to interact with AI based on age, gender, country? Is it something that you've looked into?
Thank you. This question is really interesting research question. I would actually hypothesize there would be some cultural difference in how people interact with AI, because I know there's like a few line of research that suggests how people from East Asia, actually more specifically people from Japan, they're actually more open to interacting with like AI agents, because it's in their cultural, in a cultural environment, they're just more fascinated into looking at these type of agents. So I think there would be interesting cultural difference, such that people from East Asian culture more open and to interacting with AI agents compared to people from Western cultures. And I think this is a really interesting future research question.
As kind of a follow-up or a variation of this question, Rachel asked if there's a gender difference between people with emotional and informational preferences.
Right. So in our study specifically, we did not find any interaction between participant gender and our main independent variable. So there was no significant interaction, but one reason could be that we actually had much higher number of female participants in our sample. So a low number of male participants could possibly explain this non-significant interaction. But I can definitely see with high number of sample, with a high equal number of male and female participants, we could hypothesize for a significant interaction with the gender. With female participants, again, another line of research suggests that females, they're just more open to receiving emotional social support compared to informational social support compared to male. So I'm sorry. So I can tell that female might be more open to interacting with chatbots that provide them with emotional social support compared to male users. Thank you for the question.
Oh, the next question is for Emma from Kristen. So do you have ground truth labels for classifying good and bad signals? If so, how did you go about obtaining those signals? Also, does a person's BMI affect your signals, and how is this handled in your work?
Okay, so there's kind of two questions, right? So ground truth and BMI. So I'll do the ground truth one first. So that's a really good question, and it's something I struggle with a lot because, as you can see, EMG looks like noise. It's not like the heart signal that has a very specific signal we're looking for. So often when I first started my master's, one of my biggest problems was, how do I know if this is good or bad? Because I honestly didn't know. And that's actually one of the reasons I wanted to do my PhD on signal quality, because that problem bothered me a lot. So there are a few ways we can try to get a ground truth. So one way is developing a simulation of EMG, or declaring that a certain signal is good enough because it looks good enough to the user. And then what we could do is take noise. So we could either simulate or purposely create noise and add that on top of our good signal. And then what we could do is try to see, can we filter that noise out? Can we detect that noise is there? We could add different amounts of noise to determine how much noise is too much noise, or at what point we detect the noise or can't detect the noise. So there's a lot you can do there with the simulations. And that's interesting, but I still feel like we don't have a true ground truth in some sense, because even if we did the recording in a very environmentally clean conditions, there still might be a bit of noise. So I guess we can never truly know. The other one was BMI, which is another great question, and another kind of problem with EMG research right now is I don't think there's a lot of diversity in the data. Obviously, since we are all university students and graduate students, a lot of people do studies on other graduate students who are in their 20s, probably physically fit, etc. So there's not only, I think, a lack of diversity in BMI, but also age, maybe even gender. I've seen a lot of studies that only did research on males, even today. People with disabilities or people with certain physical conditions might have different muscles than others. So there's a lot that could be done there for sure. For the BMI specifically, in terms of measuring signals, if someone has more fat over their muscle, it might be harder to get a reading on the signal. I haven't explored that specifically. So maybe not BMI, but body composition might be more of a factor there. So that's definitely something I think should be explored, and I would love to help explore getting more diverse data for sure.
Yeah, that's really interesting. So there was a question early on by Capel saying, when I graduated in 1978, there were only 2 ladies in the class, so 1%. What is the ratio of undergrads today? So there's nearly 1,150 women undergrads enrolled at Carleton's Engineering and Information Technology programs, and that represents 21%. So that's sharing that information. So Brittany, there was a question about where specifically do you do your research? And perhaps I can sort of expand this question a little bit and say sort of how has probably working from home impacted your research?
So I do my research specifically with the clock signals that we were talking about. So trying to increase the speed without getting the timing errors that we encountered today during my discussion. Most of the circuits that we work on are very small. Like by the time the system's done, it's smaller than your fingernail. So we do everything on the computer through simulations, and working at my office on campus or working at my office on home hasn't really impacted me too much when it comes to those things.
Thanks. I'll actually extend the question to Emma as well. What has been the impact of the current pandemic on your research this year?
Yeah, so for my research, I was actually supposed to go to New Brunswick because there's a really good physiotherapy school there to do research on doing my EMG with the electrode arrays. So I wasn't able to do that. So that definitely did affect me. And maybe this summer I can go there. I was supposed to go last summer, so hopefully we'll get there. But yeah, collecting data has been hard. So I've been using data sets that have been previously collected, which is still good and still usable. So it's kind of been hard not to have my own data though.
Yes, that's definitely something that has impacted a lot of us that work with real people to in the course of our research. So didn't the question is the same to you? What has been the impact of the pandemic on your research?
Frankly, Audrey, most of my research can actually be conducted online, conducting experiments. So I still have a good pool of participants that I can recruit and conduct an online experiment. So I'm not as greatly impacted by pandemic in terms of collecting data. So so that's that would be my answer to the question.
Thank you. If I read between the lines, I think sort of the impact is more on research culture and sort of the lab interactions with other people that has had sort of a stronger effect on all of our research. We can't just turn to our office neighbor and say, I'm running this problem. Can I just talk you through it? And that is very unfortunate, because that's kind of a great part of academic research life. Okay, so a few more research specific questions. Emma from Keppel, when you use multiple inputs for muscle contraction, do you use the majority rule as a filter, which is the best 5 aligned signals?
Yeah, so the majority rule doesn't have to be the best 5, but yeah, so basically if we have multiple inputs, right, then if some of them look the same or most of them look the same, we could infer that's the correct one we should go with. So I've definitely done things like that in the past for sure. And I think you definitely use that. It's not the only thing you would use, because obviously maybe all of them were equally bad. So maybe using the majority rule isn't good in a certain situation. So there'd be other factors you look into, but yes, definitely, especially with the electrode array, a common thing would be looking at to see which ones are kind of more in agreement.
Thank you. Jen, the next one is for you from Rachel. Given that information types were open to both emotional and informational responses, and emotional types needed the emotional responses, so I find this interesting that female public healthcare worker leaders in the past year, which provided an emotional as well as informational message, were really effective. So can you speak to this?
Of course. Absolutely. So, female care leaders in the last year, they amazing in providing emotional and informational support to the general public. I think it is possible that people may actually have a different expectation in their interaction with human care providers versus AI healthcare providers, such that when they interact with the human beings, they think that, it's another human being, therefore I can expect to get both emotional and informational social support. But when they interact with AI agents, although with their advanced intelligence, I think human beings also put some constraint, also have certain ideas of how these agents work. So they may actually expect to just get one form of social support rather than receiving two types of social support in these AI healthcare providers. So I hope that somewhat addresses your question.
Thank you. So on behalf of the entire faculty, I'd like to thank each of our presenters for sharing your research with us. It was very interesting, and your answers to the Q&A were very thoughtful, and it's really interesting and important to hear about sort of the work that you do and how you're currently doing research-wise given the pandemic. So if I can end with a final thought to wrap up this morning's program, is that we want more women to enter the engineering and IT fields. Above all else, we must continue to encourage them to imagine for themselves all the ways that STEM can make their bold and diverse vision come to life. And we're all better for it. We'll all be better for it. So thank you to all of our attendees for joining us today, and to our wonderful presenters for sharing their work with us. I hope you'll enjoy the video and the rest of your morning. Happy early International Women's Day.